Good morning. Can everybody hear me?
Good morning.
Awesome. It's pretty early, so I'm glad everybody showed up because my coffee just kicked in. So, my name is Derek Chamorro. I live in Austin, and I am responsible for the hardware and firmware security initiatives over at Cloudflare. So I deal a lot with hardware, so you might be asking what a hardware guy is doing talking about key management. So I've been a researcher for over 20 years now. I have a bunch of publications and patents on a bunch of different fields, primarily blockchain, encryption, and key management. So this project specifically is kind of the culmination of a couple years of research with a bunch of other teams where we kind of looked at some of the problems in this space and trying to figure out ways of integrating them into our environment and some of the challenges associated with that. So really excited to talk about it, and if you're ready, we'll get started. Standard RSA disclaimer. So key management. This is not going to be a primer on key management. I assume that a lot of folks in this room know what key management is, but we'll talk about kind of some of the challenges associated with leveraging these systems, some of the problems that companies have had, whether it be process, procedure, framework, and then kind of lead into Cloudflare's challenges, why we couldn't just kind of take a regular key management system off the shelf or a cloud provider or leverage a cloud provider and integrate it within our network. I'll get into this concept that we developed called distributed key management, which sounds kind of anti-pattern. Normally you don't export keys, right? You keep them enclosed within a key management system or HSM, but we kind of developed a secure distribution method, and hence why we call it distributed key management. The second half of this talk is all about local aspects of key management. Once an application, a service, or a host gets a key, what do you do then? Do you just kind of leave it there, or how do you protect it? And then at the end, I'll wrap it all up, package it together, show some workflows, show some of the cryptographic operations, and hopefully it all makes sense. So when I talk about key management, whether with coworkers or whether with friends and whatnot, it's never really on the latest and greatest and the coolest thing. It's usually on how companies have mismanaged their keys. We've all seen these headlines. Some of these are actually pretty recent. And if you haven't, you kind of generally get the idea of what's going on. Private key was accidentally leaked. Primary key was stolen. It was an inside job. Hackers steal a private key or seed files, or there's some kind of new hack or vulnerability that's out there. So key leaks can occur in plenty of different ways. Human error, software vulnerabilities, misconfiguration, or through malicious attacks. And so, regardless of really how it happens, it's really all the same result. Some nefarious actor has your private key, is able to decrypt data, has access to sensitive information, or worse, signs malicious artifacts. So what if I told you that all these companies had some form of key management in place? Where do you think the problem would be? Would it be process, procedure, was something misconfigured? I like to think that part of this may be due to the framework that was used. So when we think about frameworks, usually we're thinking about NIST in this document, NIST 857. For those that are unfamiliar, it's kind of covers comprehensive set of key management guidelines associated everything with the key algorithms that you're supposed to use, as well as protection requirements for these keys. It's set up in 3 different phases. Part 1 is key lifecycle management. What are the key sizes for different security requirements? The second is best practices, how to implement good key management hygiene within your organization. And the third is strictly kind of limited for applications. How do you implement these within your VPN or your email applications or whatnot? But it's missing something from this. What it's missing is resilience and scalability. It talks about key backups. What happens when your primary system goes down? How do you recover with a secondary backup system? But it doesn't cover the concept of what happens when your entire cluster goes down. We kind of see that within conventional key management systems. They're kind of set up similar to this, where they're on-prem or cloud-based or like a hybrid of both. Their primary focus is security, as they should be, but it doesn't really focus on necessarily performance or this concept of how to scale those systems out, aside from it being within a specific region or cluster. And outages are considered catastrophic because a KMS that shuts down or breaks in one of these regions usually has services that are pinned to it. And we've seen this. We've seen this in these KMS outages. Here's Amazon Web Services had an outage November 2020 in one of their US East regions that caused some customers to experience failures, not just with their KMS keys that were leveraged within AWS KMS, but with the services that relied on them, things like EC2, RDS, and AWS Lambda. So this outage lasted several hours and, again, caused a lot of headaches. Google Cloud, they had a outage in September 2020. It was a network connectivity outage that severed one of their APAC regions that, again, affected KMS customers that had their cryptographic keys stored within their KMS services. Azure had a key vault outage that occurred in March of 2021. Caused panic and pain with customers that had their keys, managed keys that were loaded into their EU regions. This one was unique because the applications that KMS was loaded on, the VMs themselves, were just stuck. They had to be rebooted. But again, when they figured it out, after a few hours, they were finally recovered. But I'm not here to make fun of 3 other cloud providers. I mean, we had the same problem. We had an outage with Warkeyless SSL service, which allows websites to hold their private keys while still leveraging our services. And again, this was caused by a bug that caused an outage for all of our enterprise customers. So we're all susceptible to it. So when it comes to challenges associated with kind of leveraging these existing frameworks, especially in a network as large as ours, I mean, it's very challenging because we're massive. I mean, people don't understand that we process more web traffic than Twitter, Bing, Wikipedia, Amazon, Apple, Instagram combined. 285 cities, there's at least 1, potentially 2 data centers per city, 192 terabits of network capacity with the goal of being within 50 milliseconds of 95% of the interconnected world. Every single service runs on every single server that we build, and that's what makes our edge network very unique. So we're not pinned to a specific region because our services live everywhere. So if we were to take that same kind of regional scalability model, where you have region 1 that has a KMS cluster here, and region 2 that has a KMS cluster here, since they don't synchronize with each other, you have to pin your applications to one, both, and have some kind of logic that allows them to be able to sustain some kind of backup. But again, in a network such as ours, where you have locations all over the place, if we were to do the same kind of concept and have these autonomous regions that don't really synchronize with each other, then a failure within one region would cause failures within all of our services. So it really doesn't work for us. So we wanted to design something that would kind of fit our global network, meet our high security standards, meet our performance standards, but we wanted to kind of build out these requirements. So to build one of these systems for a network as large as ours that's very highly distributed, had to be resilient, had to be available. Services can't be disrupted because a KMS or related component fail. If we needed to take a KMS server offline for maintenance, the services that were pinned to that should not be disrupted. Had to be scalable. I mean, we had to plan for the applications that we wanted to protect today as well as the applications we wanted to protect in the future. Had to be performant. If you're familiar with us, we have lofty performance goals, and we not just meet them, but we exceed them. So any of these services that we built had to kind of meet those lofty performance goals. Had to be secure end-to-end. I'm going to pin this because that's kind of fairly implied, but when I talk about this, we had to distribute keys not just to a host, but also to ensure that we're loading them securely. And be open source. We didn't want to pin ourselves to a specific vendor and have to worry about how we're going to kind of build that. We wanted to keep it as open source as possible, potentially open source in the future as well. So at a high level, this is kind of what it looks like. And on a side note, I actually drew this on a bunch of napkins at a bar one night, and with my coworker Michael, who couldn't be here. And I tried to find the napkins, and I think my daughter might have destroyed them. But it looks something similar to this, so you get the prettier version. So 10,000-foot view. There is a central key management system. This system is comprised of many servers that contains kind of like our main managed key and policy database. there is a tier, a service tier, known as an edge KMS tier. We're an edge network that includes a series of servers, or what we call edge key management systems. And then we have the components, the server components and applications that actually communicate with the KMS system. So I'll break it down a little bit further. The core KMS server centrally manages the lifecycle access, cryptographic operation, and administration of managed keys. So this really acts as the heart of our distributed KMS, where we create these initial managed keys and key policies. The core KMS server will periodically replicate managed keys, associated policies to this edge KMS tier or eKMS servers. So each eKMS server stores replicated managed keys and policies from the core, and will query the core KMS if a managed key is not in its key store. Furthermore, eKMS servers receive managed keys from each other or updated policies from each other. And this is in addition to the core, and this is in times where the core KMS server might be slow to respond, or if for any reason it's actually taken offline. There's a managed key that's always available. So each intermediate KMS server provides a key service to a client, things like encrypting, decrypting a data key, creating a data key pair, signing and or generating a random number. So unlike conventional KMS systems, clients can transmit a key service request via local KMS client, which is just kind of an agent that sits in our servers, to any multiple intermediate KMS servers. Again, this kind of improves resiliency in the times where there could be an outage or there could be maintenance. It's a very, very high level, but I'll break down each component. So the core KMS server is a custom-built system. We build our own hardware, and the same thing, we build our own KMS servers. It's a hardened Linux system, Linux distribution that literally only has the services capable of running this system. So it's comprised of key management engine and a policy database. So each managed key, which is a wrapper key for managed services, is associated with its own policy to enforce fine-grained access controls, using multiple attributes, things like protocol, identity, IP address. So at instantiation, the CKMS first validates a call or request to an identity service, and then it'll check against that policy if an existing managed key policy exists. If not, it drops the request. So every managed key is not just protected within the system, but it's actually protected in hardware. So we use hardware security modules. They're FIPS 140-2L3 certified modules that sit in a PCIe form factor that are used to store managed keys as well as perform cryptographic functions. Our edge KMS looks very similar, as it too will authenticate caller requests, but it stores synchronized copies of key rings and policies. Key rings are just groups of cryptographic keys or subkeys, and again, they're protected in a FIPS level 3 certified HSM. It's also used to protect the eKMS data, so things like key ring policies, policy keys, and so forth. Finally, these systems use like a replication service, and that's like the heart of this. I've always said that it's very important to have availability at all times. So we use a synchronization service that leverages a hardware-based root of trust for authentication between all these systems. We leverage TPM endorsement key certificates to do that. And then each key ring is encrypted for each individual eKMS, so that way we reduce the threat of a single key attack. So key rings are organized based off of organizational policy, business compliance requirements, and so forth. And then finally, we have this KMS client that acts as a proxy, to proxy these KMS requests to this edge tier here, as well as to core KMS. So the KMS client authenticates to the eKMS via hardware root of trust. So the whole point is that you create a data key pair, managed key is replicated within eKMS, used for wrapping purposes and so forth, and everything kind of works. So pretty easy, right? But why is it better? I mean, why, when you look at a system like this, it doesn't look much different than what you would expect to see within AWS or Google Cloud, any other KMS products. But at the beginning of this, I said the importance for us was availability. If a KMS is taken offline, or if a region is taken offline, then our services that are pinned to that region would be down. So we scale horizontally. We scale this core KMS tier, we scale this edge KMS tier, and then we replicate everything. We're not pinned to a specific core, because cores will replicate with both eKMS servers. eKMS servers synchronize with each other. so forth, and so forth, and so forth, to the point where we actually manage consensus where keys are actually created within this tier here. Pretty easy. Might be a little hard to read, but this is like a key service request sequence. So here we have an application that's querying the KMS client with an initial key service request. It's represented by KD as a data key that's encrypted by managed key represented by KM with a bound identity policy as IDK. The KMS service will first check its data key cache. In this scenario, it's not found. So it sends a request to an edge KMS. KMS client checks to verify and transmits the key service request to the edge KMS, which generates a response and allows the KMS client to update its cache. So in the second example, the application sends a key service request to the KMS client, but in this example, the edge KMS is unavailable or slow to respond. And so what it does is it forwards that request to another edge KMS or core KMS server, which then processes that request, updates its data key cache, and then services the key service request back to the client. Updates its data key cache. And this is just a sequence of how we actually manage and validate policies. So again, key service request includes an identity that sends it to an edge KMS. It verifies the identity with identity provider, determines if a managed key is available, enforces that policy, will perform cryptographic operations on that managed key, and then service that key service request back to a KMS client. And this just shows kind of like the resiliency aspect of it, where it verifies the identity, determines that the managed key is not available, will then query a core KMS server, enforce the policy, and then update that request to the edge KMS in order for it to be able to service that. So, pretty simple. That's kind of like the distributed key management architecture. So I talked about leveraging this KMS client in our distributed KMS architecture, but again, it just kind of acts as a proxy to proxy these key service requests. But what happens when a key gets to a host and or application? How do you distribute it securely there? When it comes to how we distribute keys or use keys on a host or service, for protection, we generally rely on concepts like memory safety. This quote actually comes from an article called from an NSA article called Software or Memory Safety that talks of kind of defensive techniques that are used that rely on memory safe languages, tools to prevent common memory related errors, buffer overflows, null pointer dereferences, use after free errors. But loading cryptographic keys in memory can introduce several security risks that can compromise the integrity and confidentiality of the keys themselves, as well as the data they're used to protect. So I'll show you some examples of that. So when we think about memory, we think about Linux address spaces. So here is a bunch of RAM that's divided up into 3 separate processes. You have kind of main logic, data, libraries, stacks, with the idea that anything within that address space can access anything in it, because it's really just considered flat. The same can be said with the kernel. It's just a flat address space. Libraries can access the stack, driver code can access core code, and so forth. But applications cannot access the process space of another application. And the same can be said that these processes cannot access, the process space of the actual kernel space, and that's kind of known as more like user space, kernel space operations. So user space operations cannot look directly into the kernel outside of like an approved or well-defined means. So when we zoom into the process space itself, look specifically at the data, we can kind of expand on what kind of data it might contain. So from a high-level view, it's usually divided into like three or four different categories. Let's just define 3. The first is kind of capturing internal state of the application itself, maybe like some business logic or some other form of intermediate data to keep track of code changes and such. Then if your application processes user customer data, it'll keep track of user customer data there, might have several copies of that data. And finally, if your application performs any cryptographic operations, it'll have cryptographic keys. Make sense so far? But because it's in the same address space, and since it's all flat, if your main application code or its libraries become infected and become malicious, then all your data is considered compromised. Again, flat address space, because that code can basically access anything, right? So really, really bad. But, you have to consider that all process data is kind of different, not all data is created equal, Sometimes it's not a big deal. So what if an attacker has access? You have some kind of public database like Wikipedia. You could probably recover from that. It's not all bad. It only really comes bad if, that attack can, it change the internal structure of your application, leading to things like further privilege escalations. But if your user data is compromised, then it can be pretty disastrous. We all know what happened to Equifax, right? Equifax, pretty bad. Caused a lot of pain. It was kind of disastrous. Cost a lot of money to recover. But at the end of the day, it's kind of still recoverable. I mean, Equifax is still a company. But if your cryptographic keys get compromised, then it's considered game over. It's usually a full data integrity compromise. So why does this happen? Why do cryptographic keys get leaked? There are a few number of ways, but usually it's related to a vulnerability, and this is kind of like what happened with Heartbleed. So understand how it happens. One of the typical ways is if your application processes some form of untrusted input and can allow out-of-band memory access. So the way it usually works is you have some stuff in your process address space, in your memory, which is needed for your application to function properly. But because it's a flat address space, you might also need to process some form of cryptographic operations, so you have your cryptographic key written nearby. In normal cases, your code can only access like the non-important stuff here. But as it happened with the Heartbleed attack, because of the lack of input validation, the attacker was able to trigger your code into reading past the stuff buffer and the cryptographic key buffer and then link it back to the user. So, bad, right? Vulnerability, how do you fix that? You just fix all the bugs, right? That's what you do. So it's like simple solution. You fix all the bugs, but sometimes it's not that easy. What if you inherited like legacy code and a patch might break your application? Or how do you count for like zero-day attacks? I mean, that and a patch hasn't been released. Sometimes it's really not that easy. But there could be a variety of reasons. So, we look at other ways that we can kind of mitigate this. And one of the ways we can like mitigate this whole class of vulnerabilities, if we look back at the process space, is that people will create like something called an agent model. And what that is that you create another process and you move your cryptographic keys from the main process to the secondary process. And then you have to build some form of logic between the two processes, and what that usually is a well-defined interface. And this well-defined interface is usually like a key. So process 1 becomes our main agent, process 2 becomes our cryptographic key. So key agent model, which is just a main process and a helper agent, which communicates through this well-defined interface. And what it does is, because of a process-based isolation, the main process communicates with the agents through this well-defined interface to perform kind of cryptographic operations. So instead of getting the key to the agent, it'll just say to the agent, hey, can you encrypt this data for me? Or hey, can you sign this data for me? And this model allows your main process to handle untrusted input and be more network-facing, and the secondary process to be completely stripped down only to handle cryptographic functions. So, makes sense, right? There are problems with this model, though. I mean, first you need to develop and maintain 2 programs and processes. You need to create this like well-defined interface between the process and the agent. You need to add communication support between the 2 processes, things like Unix sockets, shared memory, et cetera. And then you have to figure out how to authenticate this, because you don't want some random arbitrary process accessing your cryptographic keys. So agent model is kind of good from a security perspective, but not really as like flexible as we'd like to be. So then we get into the Linux key, kernel key retention service, or simply the Linux kernel key store. So what we do is we take this process 2, and instead of having this process 2, we just replace it with Linux kernel. I mean, why not? I mean, we're already running on the Linux kernel. We don't have to start anything since the kernel is already running. It's already considered well-defined. Otherwise, process 1 would not be working. And then we replace the well-defined interface with system calls, because syscalls are already built in. They're already well-defined. They already work. We don't have to worry about them. So Linux kernel key retention service, it stores keys as kernel objects. It was initially designed for file disk encryption, for sharing keys with kernel services, things like LUKS, DMCrypt, TEncryptFS. can be used by user space programs to manage their keys and secrets. So keys are stored outside of the process address space. There's already a well-defined system call interface for access and to use keys. So you can implement specific types of security policies, things like LSM hooks. And you can bind the key lifecycle to the code lifecycle. So you can implement things like key auto-destruct. So when a process terminates, you can zero out the key in memory, even if your process is written in Java. And these slides will be available. This is kernel documentation. It's really available for anybody to kind of read. So if you look into the Linux kernel key store, you have to understand some terminology. I talked about key rings previously in a distributed KMS architecture as a method of grouping keys by policy. Key ring object within the Linux kernel key store is similar, that it contains groups of keys, but it can also contain reference pointers to other keys. And a key can also be part of 2 or more key rings. So you can create this kind of like nice key hierarchy based off of permissions. So again, keys, cryptographic material, a pointer to it, used to perform cryptographic operations, obviously. It can be different types, user or session keys, and it looks very similar to a file system. Key rings can contain links to keys or other key rings, so if it's not present, then it'll be securely destroyed. Represents a collection of keys, can be explicitly created through threads, processes, users, or sessions, and then you can force things like lifetimes for key rotation. So I previously talked about address spaces and how we want to prevent a key from being in a process address space from the application, but say you have something like an SSH user script that leverages the Linux kernel key store, takes a key from a file, after it executes the script, it wipes the key from memory. There still exists this small window where you might, the application might crash, or you might do a core dump and leak that key material. So how do we provision application keys without the cryptographic material ever being exposed to user space applications? There are a few key types that are available in the Linux kernel key store. We'll talk about 2 of them here. So one of them is called encrypted keys, and the idea behind that is that say you already have an application that has an encrypted key, or that you have a wrapping key. This is the kernel key ring, and the application has an encrypted version of that wrapped key. So what the application can do is add that key to the Linux kernel key store, and the kernel will transparently unwrap that key using the wrapping key inside the kernel. And it's encrypted in user space, but it gets decrypted in kernel space. So if we try to read it back, or another process tries to read it back, they'll just get a version of that wrap key. There's also the notion of trusted keys. So very similar to encryption keys, but instead of the wrapping key being stored in the kernel, it's leveraging like a trusted platform module or TPM if it's present on a system. So again, you have the wrapping key wrapped by the TPM, and you send it to the kernel to transparently unwrapped in kernel space, and if you read it back, it'll be wrapped again in encrypted form. But because TPM operations can be slow, we can create kind of like this combined schema that enables this rudimentary local key distribution system. Here we have process 1 and the kernel key ring, and what we have is an additional helper provisioning process, as well as leveraging a KMS which stores a root key. From here, we can send it in a wrap form where it can be stored in a TPM, and then send it to the kernel for unwrapping, and then each application can request from the KMS its own application wrap key, which can insert into the kernel key store, be automatically unwrapped, as well as using like this stored root key. So in this scenario, the plaintext cryptographic material is never exposed to user space. But there are kind of still problems with this approach. The applications are still responsible for contacting the KMS to get their wrapped keys, which can kind of like create this bad user experience. Since each application would need to know how to communicate with a KMS, and especially if you have multiple KMSs, you'd have to provision that within your applications. And there's little administrative control on the kernel key object, so something like invalid key permissions could accidentally leak a key. So how do we mitigate that? This is something that kind of everybody can do. There's the Linux kernel key store provides 2 system calls. What we've been using now is the add key system call, which adds the key to the specified key ring on behalf of the application, and with the provided payload. So the application provides the payload, whether encrypted or not, and the key ring then processes it. But there's another system call that we can use and this is called the request key. The difference is that the application doesn't provide the payload to the kernel. Instead, it requests that the kernel deliver that key to the application with the kernel providing the payload. So this can create a lot of load on the kernel, but what the kernel can do is create a helper program in user space to assist the kernel. This is kind of where we hook in our KMS client and hook in our external KMSs and add our key permissions. So it's nice because it's a single centralized OS API to request keys. You don't have to do any connection strings. You just a free-form string ID, decouple from key storage backends, and it's a more secure way to transparently add keys to a key ring. And again, here's the documentation on it. So to see how this works, when a process needs a key, it doesn't need to have any URLs or HSMs in the code or protocols in the code. It just needs this free-form ID. So in this case, our process wants to access Cloud App Key 1, and what it does is issue a request key syscall, and what the kernel does on the application behalf is create a placeholder for this key. So then, because it doesn't have any cryptographic material, it calls out to a special user space helper program, which resides at SBIN request key, and most Linux distributions have this standard implementation that allows you to write submodules where we actually are able to implement our KMS client. And then each submodule can be involved based off of the key path and the application requested. So in this case, the request will invoke the Cloud Star module, and that module can contact our KMS and ask for that specific key. So in turn, once the KMS returns the payload to the request key helper program, the program then sends the payload back to the kernel with the key, and the kernel notifies the application the key is ready. So this schema allows us to kind of treat the kernel as a trusted execution environment, which can further be extended by leveraging things like a TPM for storing additional keys, wrapping keys, things like cache, machine identity keys, and so forth. So, make all sense so far. A couple different components: distributed KMS architecture, the localized distribution to be able to instantiate and create secure keys. So how do we specifically put it all together? So we have 3 environments that represent different boot phases, with our TPM kind of being our hardware anchor for our trusted execution environment and extending this into the Linux kernel. So first we have an application asking the local KMS client to unwrap a data key. And it's represented here by KD and our key encryption key, and it's bound by this identity policy. So the KMS client will forward that request to a primary KMS server in order to be able to process the managed key for unwrapping. And again, we have a secondary Edge KMS server, or the whole slew of Edge KMS servers that we use in case the primary server is down. Unwrapped keys are cached in kernel memory, as represented here by our data key cache component, right there. And cached keys are protected using cache encryption keys. So the key store is used to store key encryption keys, and then used by applications to protect data keys, and then the key store is protected using its own key store encryption key. And then where do we all store those? TPM. So TPM to store device management keys used for wrapping, the key store encryption key, cache encryption key, and we also use a TPM endorsement key certificate as a method to authenticate the machine and the KMS client. So here's some of the KMS key store operations. I just processed a couple different workflows for anybody that was interested in the cryptographic operations. Here we have 2 key operations are represented here. So workflow 1 shows an application sending its data key, as represented by DKC I, which is bound by an identity policy, and the unwrapping is done locally by the key store, right there. And then the application key, which is represented as KCG, unwrapping is done remotely by an eKMS or service KMS. Workflow 2 is similar to workflow 1, but we have cryptographic operations represented by PCI right there. This is an example actually of decryption of ciphertext or digital signature generation performed within the key store itself, and then the unwrapping performed remotely by a service or eKMS. So, kind of just wrap it all up. Keys still get mismanaged, not necessarily leaked, but they get mismanaged. So companies still experience problems with that. we like to think that maybe it's not just a misconfiguration. Sometimes it's based off the framework. If a KMS is down, their services go down. There's potential for key leaks and so forth there. Need to update for modern KMS frameworks, especially for edge companies like ourselves. We just can't take something and lift and shift and put it and retrofit it into our network. We needed something that was going to be a little bit more resilient. And that's what brought us to say we can build fully distributed KMS systems where we create this replication tier that allows key objects to be replicated across a whole fleet of KMSs. And then once you actually get a key to a host and to a system or to a service, how do you load it securely? How do you ensure that you can prevent kind of against the next Heartbleed attack? By treating keys as kernel key objects, and we feel that's the better method of being able to protect application keys. So all this work we blog about. So please follow our blog. Every phase of this work is actually getting blogged about. Every stage is getting blogged about. Here's my website. I do a lot of different security research, random musings and whatnot. And then I'll be available for taking questions like after the talk, here or outside, and then also at our booth at S960 or S960. My eyesight's starting to go, so I'm sorry. Yeah, S960, back of South Hall. You'll be able to find me there. Yeah, I think that's it. Thanks. If y'all have any questions, you can just ask the mic, or if not, just ask me privately.
Yeah, so I have one question related to this backend key store.
Yep.
Is it per region, or do you have just one, or how does it go?
So within our core KMS tier or Edge KMS tier?
Yeah, the core KMS system.
So it's actually a custom-built system. So it's a custom-built database that allows us to be able to replicate, and we use a separate key per managed key in order to be able to replicate those keys across a series of eKMSs. So it's a custom-based system that we built using a lot of open source components and some of the components that we're actually building as well. We manage consensus in that core KMS tier. So the question is, how do you manage consensus amongst hundreds of machines? We only have to manage it within that core KMS tier because that's where the initial keys get created. So when we replicate those out to that Edge KMS tier, so all they have is replicas.
Right. I was actually coming from the geolocation or geofencing point of view. Like your
Yes.
data is not, you are not allowed to replicate data like just anyway. So for the keys, how does it work?
Great question. So those are identity and policy bound, and then we leverage our network. I can't talk about V2 of this yet, but we built a custom protocol and a custom service, which hopefully we'll be talking about at Black Hat on how we leverage additional key protections from like a privacy perspective. Right now we leverage our network and that policy that states, that tags and labels where a key should live. But think about things like eKMS and leveraging your own KMS servers in order to be able to send the request and process it to where it needs to be.
Right.
Yeah.
Okay, thanks.
Yeah, no problem. Any other questions? Cool. I'll be available around here or find me at the booth, and thanks again.